problem. Is there anything additional? All right. So we would like to challenge problem number 5, bimetallic oscillator.
All right, problem number 5, bimetallic oscillator has been challenged. You have 1 minute time to either accept or reject.
We reject it.
All right, bimetallic oscillator has been rejected. You should, by the way, sign after me. No, that's fine.
We'd like to challenge problem number 10, droplet explosion.
All right, droplet explosion number 10 has been challenged. You have 1 minute time to decide.
We accept.
All right, problem number 10, droplet explosion has been accepted. You have 5 minutes time for preparation.
the following statement states that when a drop of water, a water mixture, for example water alcohol, is deposited on a surface of a hydrocarbon liquid, for example vegetable oil, the resulting droplet may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplets. So I'd like to begin with a phenomenon demonstration. So this is us actually dropping it, and this is the droplet fragmenting into smaller multiple other droplets. So you go to the next slide. So we've already done the phenomenon demonstration. We will then continue the experimental setup, the explanation, the mathematical modeling, and the data analysis, which comes together, the conclusion, and then how to finally start the business. So first of all, we obviously use a microscope camera, which is connected to our laptop, a micropipette, some sunflower oil as a hydrophobic liquid, as well as the water alcohol solution, which was IPA. And then we used this other setup, which was mainly for the preliminary observations and to collect the final sample size of the number of droplets, because this microscope couldn't take a picture of the entire dish. And then we used image analyzer to analyze the final number of droplets in the image, and also the size of those individual droplets, as well as a ratio to the pixel size of the screen, which we then use to calculate their actual size. And then finally we use tracker to track some other aspects of the droplet, of how the mother droplet expanded and receded. Okay, so a simple explanation of the phenomena is that when water is dropped on a hydrophobic surface, it tends to form a straight angle with the hydrophobic surface itself. It does not wet the surface at all. When alcohol is dropped on the same surface, it tends to spread because of the different surface tension, and alcohol also evaporates. Similarly, what happens in our case is that the alcohol starts evaporating, and then slowly and surely this process decays into the fragmentation we saw earlier and the formation of these perturbations. I'll explain them as we go on further. So first of all, the spring ring instabilities form, and then they grow larger, and then they fragment off into smaller droplets, such as the one in this picture. Okay, so one thing that is absolutely essential for this process to happen is something called the spreading parameter, which is just the force of adhesion minus the force of cohesion, which can be written in surface tension. So it's basically the surface tension of the mixture and air plus the oil surface tension plus the surface tension of the mixture oil interface minus 2 times the surface tension of the oil itself. And so this gives us this final equation. And so as you can see from this graph that was taken from literature, this phenomenon only takes place when the spreading parameter is a non-zero value, which according to literature was at 0.35, and it's pretty close in our actual experiments as well. Next slide. So one thing that happens here is that the part in the middle has something we call the initial concentration, which is like the concentration of alcohol our original solution had. And on the sides of this mother droplet, we have something called the critical concentration, which is like the minimum concentration needed for this process to work, which was like discussed when discussing the spreading parameter. So because of this difference in the volume, the percentages, there is surface tension gradient basically. There's high surface tension on the sides and lower surface tension in the middle. This is what causes the maroon effect, where the liquid moves from the middle to the side part. Next one. Okay, then there's also evaporation happening because IPA is quite volatile, and so it evaporates relatively quickly. So these are graphs that are taken from literature for the evaporation of IPA, and they basically present different values. And as you can see, as we increase the concentration, the evaporation rate decreases greatly. Okay. So one thing that we need to keep in mind is that the radius of the mother droplet can be calculated by the following equation, which we also took from literature, by balancing the shear stress, by balancing the shear and the viscous stresses on the liquid in the mother droplet, we can come up with an equation. equation for the Marangoni velocity within the fluid, the Marangoni velocity of the fluid for when the radius of the mother droplet is at its maximum, which we can calculate by using this formula. Okay, so we did practice by solving paper slips in the mother droplet itself, and we could come up with a somewhat accurate measure for the Marangoni flow velocity and the trend line that we got from our equation. You can see that it does follow the general trend, though there are a bit some inaccuracies. Okay, so let us go over to the droplet column formation. So something that actually happens is that these small columns, well, they are very visible in the picture because of contrast, but they start forming, and they're essentially like these columns presented here. And the distance between those columns was surprisingly close to each other. In those columns, it was more or less the same, which we denote as lambda. So what we imagine is happening here is that we imagine that the rim of the mother droplet serves as a cylinder that encapsulates the overall droplet itself. And so by imagining it as a cylinder, we do already know that the velocity within it is the Marangoni flow velocity, and the only other thing that we believe is like actually causing it is like a capillary pressure. So by using the Young-Laplace equation, we can set the surface tension and the Marangoni velocity equal to each other, and by like further introducing viscous drag and solving this equation, we can come up with a value for the rim radius, which is the radius of this circular rim of concentration 0.35, or the critical concentration is that encapsulates the entire mother droplet. Next slide. And we already have this graph of Marangoni velocity, which is a part of the equation for rim radius, and we could further use it to calculate rim radius and compare it to values from literature. And there is somewhat of a close correlation between those values and what we calculated. The trend line represents the values from literature. Okay, so now the next step is like how do those perturbations that form in the cylindrical rim, in the so-called cylindrical rim of the mother droplet extend further into like these big perturbations, which then themselves break down into smaller droplets. So over here we assume from literature again that the value of lambda is 9.1 times the rim radius. Now this is shown with the really Taylor instability that this does indeed happen, and now this allows us to find out the number of columns formed, which then gives us the number of droplets and the average droplet size. So over here, just for the case of simplification, even though the rim isn't a perfect cylinder, we just assume that lambda is still equal to 9.01a. Next slide. Okay, so furthermore, something that did come into my mind was that if the rim does actually experience gradually instability, then it should have a different capillary wavelengths for different perturbations. And the following formula can be used to calculate such perturbations, where the surface tension of the mixture oil interface is divided by the initial density of whatever the mixture is, the water atom mixture is, and then that is subtracted by the density of the oil and multiplied with the gravitational force. And this should give us, in theory, the capillary wavelength, which we could only calculate by literature, and but mainly we tried to solve it, as you can see, it wasn't really that accurate. So going on further, if we keep the assumption that lambda is in fact equal to 9a, we can then use the equations for the graduating instability that come about from the critical time, and we could just put it, we can use it to calculate the critical frequency of each and every perturbation, which is just 1 over whatever the critical time is, and we get the following equation for that. Okay, so now that we have the equation for the frequency of the droplets formed by a single perturbation, we can then get a general trend for what's actually happening. And one thing that our equation does, could actually show is that even when the rim radius decreases exponentially with that, so the frequency should hypothetically increase exponentially, and hence we should have an exponentially large number of droplets once we increase the concentration, which can be somewhat seen from our graph here. Okay, then the next thing that the problem statement told us to find out was the size of the final droplets. And the average area of the final droplets is just the concentration of water. Is this the concentration of water multiplied by the initial volume over the number of total droplets. And hence we plotted the average droplet size over the number of droplets that were actually there. Go back, please. That were actually there, and we found out that the number of droplets formed decreased very largely. Whenever the number of droplets increase, the average droplet size decreases. Okay, and we also found out that the number of droplets formed don't really increase that much, and the volume of decrease a lot when the volume of the final droplet increases. However, the size of the droplets don't really change much, which does make sense. Okay, so just to summarize the spreading parameter and the manual flow velocity, and then we reduce the capillary pressure equations and we use them to calculate the rim radius. Next slide. And then when setting lambda is equal to 9a, we were able to get the critical frequency from which we could calculate the number of droplets, the size of those droplets, and the average droplet size, all that. Okay, and these are references. That's it. Thank you.
So I just want to confirm, you use really pattern stability.
Yeah.
And did you measure the concentration of isopropyl at the end of the droplet? At the edge, did you measure the concentration?
No, I just use literature to confirm those values.
Okay, so you do know the surface tension at the edge? Surface tension at the edge?
Yes, those values were taken from literature. Yeah.
And can you go to page 20?
Yes, sir.
So is the green line the theoretical?
Yeah, it's a turn line.
Why isn't it smooth? Why isn't it smooth? It seems a little bit jagged. Why is it not smooth?
I guess there was a problem with rendering it, but like it should be smooth.
Okay. And can you go to page 50? So how do you measure the flow velocity?
Do you mean the trend line or like the
On
output?
the actual experiment output.
Oh, we deposited really small paper sets and then we used a tracker to calculate.
Oh, you use
tracker.
tracker.
Yeah.
Thank you. And what's the thickness of your oil?
It was kept constant at like 8 millimeters.
8 millimeters.
Yeah.
Okay, thank you. And did you observe that when the final droplet gets ejected from another droplet, does its size change with time, or does it just stay constant?
Could you please repeat the question?
Does the size of the final droplet actually change after it gets ejected? After it leaves another droplet, does its size change?
There are multiple final droplets, and yes, their size does change.
Their size does change. Okay,
Yes.
thank you. And is the condition for spreading and fragmentation the same?
When, yes.
I remember like you saying that, you have a plot saying that at the critical concentration it fragments and it spreads. So you think the condition is the same?
Yes, when it spreads, it also fragments.
Okay, thank you. That's all.
Yeah.
Alright, thank you very much. So you have 3 minutes time for final evaluation.
only another droplet explosion. So in another observation, it's noticed that when you drop the droplet onto the oil, it explodes at fractal. Their setup, they use isopropyl solution mixed with water, and they use a microscope to observe the number and the size of the final droplet. We use it analyze software, and we think that's really good because you can take observe both the size of the number and plot the size of the number to see the distribution of the final droplets. This is idea for why spreads is not introduced here, so we don't actually know why this is important. And they didn't mention they added a dye to the final droplet, but it didn't explain the effect of a dye in this setup. Okay. And for their explanation, it said that the alcohol is actually more miscible with the water and oil, so it allows the mother droplet to spread more. And it has a different surface tension. Okay. And because alcohol evaporates fast, so it produces a surface tension gradient in the droplet, and then induces the Marconi flow outwards. And also, they explain that the dollar droplets form due to perturbation at the rim of the droplet, and that grows exponentially into the final droplets. So we think all the processes are explained, but they didn't explain the current conditions for fermentation and spreading. So we think actually that the condition for spreading and fermentation might be a little bit different. And for modeling, they said that the evaporation rate is concentration dependent. And they use the scaling law, which is cited in literature, and they also introduced a Rayleigh time feasibility to discuss the size of the final droplets. So we think the pros are eventually concentration dependent, but it wasn't actually used because in the reference, the evaporation rate was assumed to be constant, and there's a lack of derivation. So why don't we just get the formula just saying a law of the mother droplet, and the conditions where the for the greater scaling law actually applies is not stated. And also, for the final droplet, they explain that because fluid accumulates on the rim, there's a small region, and they use the Young-Laplace equation to derive the capillary pressure at the rim. And this balances with the inner viscous tract of the oil to give them the thickness of the rim. Thickness of the rim radius, and this is a numerical theory which is very good. But they didn't actually measure the concentration at the end, so the calculations might be a little bit different. The value was taken from literature. They didn't confirm the concentration. There's a lack of error analysis. And the unit was, the unit for the plot of the final droplet size was not actually shown. And there's too few theoretical points. So we think that's the reason why the data, why it didn't render actually a smooth curve. So for discussion, I want to discuss the time dependence of the dollar droplet and why you get distribution of the sizes. And I also like to mention that the spikes also merge together as the droplet expands and shrinks. And for the experiment, I would like to discuss how the concentration at the edge might be different from what you got from literature and what the actual effect of the oil is. And for the modeling, I would like to discuss how this might affect the Rayleigh plateau equation you use and why is that actually applicable to this scenario. And the conditions of spreading might actually also depend on the oil. So this is the thickness of the oil is also very important to this experiment, which I think you didn't actually change or show us. Okay, so I would like to begin my discussion.
All right, thank you very much. We will move on to the discussion time, where we will allocate the time until the presentation is connected. So please pause your cluster. Thank you. All right, that's good. So we will continue.
Thank you. So during my short question, I asked that whether when after the droplet is expelled by it is detached from the droplet, its size changes, and he said yes. So
yeah, okay. This is a really fun phenomenon here. So when the final droplet, there are multiple droplets that are being ejected from the rim of this perturbation, right? All of these droplets are not entirely water by the time they're ejected. Yeah. So the thing is, even
there's still like IPA in this.
Yeah, there's still some trace amount of IPA in this. But like when the time for the experiment lapses, a few seconds after that, we noticed that the size of the final droplets did shrink a bit. But we realized that was just the remaining IPA evaporated. So
this is because of evaporation.
Of IPA, yeah.
Okay, of IPA.
Yeah.
Okay, so do you think like the concentration at the edge is constant throughout the entire experiment? or does it actually change? So for example, for like 1 second into the experiment, you get like a concentration of 50%, and for like 3 seconds into the experiment, you get a concentration of maybe something lower, 40%. Do you think this is possible? So the concentration for the final droplet is actually different at different stages.
Yeah.
So do you think that actually?
No, because like if in the
Yeah.
okay. So if the final concentration in the rim would remain the same regardless of what your initial concentration is,
Yes.
it shouldn't make sense that that the size of the final droplets would be any different from each other. Yes, their amount could be different, but their size wouldn't be. So yes, I agree with that.
So great. So I would just want to clarify. So you think the concentration at the edge is constant?
It is a constant for as long as the perturbations don't start growing.
As long as the perturbation.
Yeah, until that point in time, I believe that it is a constant.
But in your theory, you solve the calculator pressure and you assume that concentration to be a constant. But here you observe that the size of the final droplet is actually different. So you have a gradual negative distribution. The number of the droplets to the size of the droplets to the number of the droplets.
Yeah.
So because that theory doesn't actually predict a distribution of the final droplet, it just says that all the final droplets are the same, right?
Could you please repeat that?
So your theory predicts like the final droplet should have all the same sizes.
No, my theory does not predict that.
So,
My theory predicts that the size of the final droplets is dependent on the initial concentration largely,
Yes.
and also the number of the final droplets.
oh, I mean like for the same experiment, the sizes of the final droplet will be the same. Okay. So I think like if you observe how this evaporates, you will get like very large droplets at the end when the final droplet springs in, and you could observe actually in your experimental observation video, like the initial droplets are very thin. So I think this is because the concentration at the edge isn't actually a constant. So maybe it will be higher in the initial part of the experiment, and then it will be lower. So that's why you get like a larger droplet size than the initial, in the later stages and a smaller size.
Yeah, but like by the time that the experiment actually ends, we believe that the IPA even in this droplet would have evaporated, and most of it would have evaporated. But just to be extra careful, that is why we took the average size of the overall droplets and not the size of the individual droplets.
I agree too.
And yes, I do agree with you that
The concentration may
the concentration there, yes, it does not stay constant throughout the entire
So this may be the
time.
reason for the distribution. Okay, this I would like to now to discuss what's the purpose of the oil. What do you think is the exact purpose of the oil?
Okay, so the oil is basically thank you. So the oil basically serves, well, in my opinion, two purposes. So first of all, the oil introduces a surface tension gradient.
Yes. And use the surface ingredient oil.
No, it's not the oil itself inherently which introduces the surface tension gradient. It's that when the
Oh.
droplet interacts with the oil,
Yeah.
a surface tension gradient is induced there.
Because of evaporation, I think. I think it's because of evaporation. It induces the surface. Wait.
It doesn't really make sense that evaporation would reduce the surface tension gradient.
You think evaporation doesn't induce the surface tension gradient? So what induces the surface tension gradient?
No, I mean the droplet itself already has water and alcohol, so it has some of its own surface tension, and then the interfacial tension.
Yes.
Between this and the oil already does exist.
How does oil produce a surface tension gradient? How does oil produce a surface tension gradient?
The forces of cohesion, adhesion of the oil actually.
May I?
Yeah.
So, I think that the main effect of the main cause of surface tension gradient is not actually oil. So from the literature side, I believe it's actually like when the droplet touches the oil, it spreads out like this. And because the ethanol has the same aerial evaporation rate, so the evaporation rate is the same. But because this part is thinner, its water concentration will actually be larger because the amount of alcohol that evaporates, the fraction of alcohol that evaporates is larger. So the water concentration of water will actually be larger.
Yeah,
so surface tension will actually be larger here because there's more water and water has larger surface tension. And this part is different, so the amount of water is actually less. There's more IPA. So this part will have less surface tension and that will drag this out. I don't think it's
I completely agree with you, but when you first said that it's the oil which induces the surface tension gradient, my initial thought was that yes, it's the oil. The introduction of the oil is what induces the surface tension gradient between the water droplet and the oil itself. But it's not actually the oil which introduces a gradient within the droplet.
Yeah, within the droplet,
That's
this is
evaporation,
evaporation.
obviously, yeah.
Yeah.
I think I explained that pretty well.
So I think like a better word for this would be like it's not a gradient, it's just the surface tension upward. And that would
I mean, that's basically the Marangoni effect.
very perfect.
Yeah.
So do you think that oil is an important parameter in this experiment?
Yes. I do believe. The
What-
height of the oil and the viscosity of the oil, both.
Yeah, so do you think that the changing of oil, okay, it would like cause an effect of fragmentation? So when I think of this phenomenon, if the oil is very thin, for example, if the oil is very thin, then the flow outward will be very difficult.
Very different. In fact, if you could go onto the slide with the equation for the Marangoni velocity. This one. Could you like press it to the animation place and you will have to have it. Yeah, so you see that the final equation, it doesn't take into account the height of the oil.
Yeah, that's the velocity of the spreading, right?
That's the velocity of the
Yeah.
spreading, but obviously if the height of the oil is not sufficient enough, so spreading would not occur within the droplet itself, within our like.
Well,
Does
this
it
isn't
have
like
that-
when it will, you just mentioned that it will spread depending on the spreading coefficient. The spreading coefficient doesn't depend on height.
Well, yes, it doesn't.
Yeah, so I don't think like oil is the oil thickness is the condition for spreading.
Oil thickness is not the condition for spreading.
Yeah, because you just mentioned that the spread is determined by the spreading coefficient, which only depends on the surface tension of a different material. So I think like what the actual purpose of the oil is. So at the edge of the droplet, maybe the concentration is very low, so it doesn't expand anymore. But in your experiment, you could actually observe that the final droplet moves out from the that the final droplet moves out from the other droplet. And this flow, I think, is actually caused by the convection in the oil. So by the oil, so there's a Marangoni flow in the middle that actually drags the oil, and the oil has a momentum and that carries the final droplets away. And I think this is also a condition for spreading, because if the oil is very thin, then all of the final droplets wouldn't be carried away, it would just accumulate here, and then would not
Basically, what you're suggesting is that the presence of the oil has a lubricating effect.
Yes, it carries the double droplets away, and if it doesn't lubricate enough, then it will just get that rim and there will be no fragmentation. Do you think that's a reasonable,
I mean, that is pretty reasonable, but like that is also like pretty well incorporated into the Marangoni velocity. So
that's
I see like what you're trying to
that's not
have here.
fragmentation.
Yeah.
Okay, so what this actually tells us is that I think the condition for spreading and the fragmentation will be different, because as you said, spreading only depends on the spreading coefficient at its edge, that is the 3 gammas.
Yeah.
Okay.
So like whether the okay. So what do you mean? Okay, I have a question. So you've been like confusing spreading. By spreading, what I only mean is like you have this droplet, you have like this surface of oil,
Yes.
and there's like this droplet over here. And so whether or not if the droplet, let's say this is the initial level, this is
Yes.
see the droplet
Yes.
folds, and this is like the droplet after.
Yes.
Afterwards, when like it's this is like spreading.
Yes, that
Like
is-
the droplet has spread.
Yes.
But like this does not necessarily say that the droplet is fragment, and I believe I did not mean.
Can you go with that? The page of the critical conservation, I think.
Yeah. Next second.
Okay, thank you. So, but I actually think that the thickness will affect how it reacts.
And I 100% agree. Like the equation of thickness, so the thickness will affect. Yeah. You mean?
But this, because you said,
Yeah.
I remember you said here that you actually spread and fragments at the same time. So I think that's actually so to clarify that these are 2 different conditions, the spreading and fragmentation. Yeah, so we
But
have
like for most cases, it happens side by side. So
for most cases, but for thin oil, just might not happen at the same time.
All right, thank you very much. You have 1 minute time to summarize.
Okay, so in our discussion, we talked about the time dependent concentration at the edge of the droplet, and instead of assuming the concentration to be constant, like the literature and the reported second, we observed that the size of the final droplet actually changes, and that is because as it evaporates. And by observing this change, we believe that the concentration at the edge is not a constant. So this actually this tells us that the rate of stability, putting in the gamma for a concentration might actually not be a constant. And then we also discussed the effect of the oil, and one of the main points is that the condition for spreading fragmentation will be different, because the spreading only depends on the spreading coefficient, but the oil actually takes the final droplets away. And if the coefficient is not enough, it will gather at the rim, and there will be no fragmentation. So that concludes most of the main point of my discussion with the reporter. Thank you.
All right, thank you very much. We will have 3 minutes time for questions on the review of these.
No, I don't know if you did the size. That was just to provide a scale for like the final measurement. Yeah.
And what is the diagram for the track area representing here?
I mean that's the value of a droplet
Is
parameter.
the stable line for the unit A T over L and T over B?
Wait, what?
Or the diagram here?
I mean, it's just a representation of what I did, basically.
Okay, thank you. And for the smart 14, what is the velocity m that you represented?
Could you?
Slide 14.
It's a manual velocity.
Okay, thank you. And in the comment, can you say what happens to increase the carbon in the alcohol?
Increase the what?
Carbon in the alcohol.
Carbon in the alcohol. Oh, so if you increase the carbon, it will be more miscible with the oil, so the spreading will occur easier.
So you need the fermentation of the droplet?
Both. The fragmentation, you will get smaller final droplets.
Okay, thank you. And what do you think?
I agree with the observation.
Do you think the fermentation of the droplet
Yes.
is smaller? Okay, and which part of the droplet is richer in alcohol?
Which part of the center of
The
the
center.
droplet?
Oh, was it two?
From the
Okay, yeah.
Thank you. And do you think the change of the size in droplets have a special rhythm or change?
Yeah, I mean, it does depend on the concept. Do you mean for like a single droplet or like for
The large droplet. It has
a single droplet? Yes, it does have a rhythm, but like the final
Do you
size
think it has a
is
stable rhythm for the change?
You mean like the shape you plot it
The
entire?
fermentation, it does have a stable rhythm.
You mean the shape?
On the droplet.
Yes, I believe my literature is having it is a certain shape.
Thank you. And with what rate the droplet they fragment? By this with what rate?
I believe it was an exponential.
It's not. You did not mention the range of the fermentation of the droplet.
I believe I get your question. Could you rephrase it and perhaps?
Okay, it's fine. And alcohol concentration is in the middle or the center of the model droplet?
Alcohol concentration because overall, but like in the middle is the initial concentration and on the side is the critical concentration.
I think in our discussion we observed that the size of final droplet changes. So it's from literature and what the reporter said is the concentration is constant, but it's actually not.
Okay, and did you consider the thickness? Because you mentioned that the shape of the droplet that you have is cylinder, right?
Yeah.
So you measured the thickness?
Of the droplet?
Yes.
No, I just made it like the size and area for you.
Don't
All
you
right,
think?
sorry, time's up. We have to stop you there. We have 2 minutes time for final questions.
Now, the statement of questions asked us to investigate the parameters that gives the experiment. Now, for an overview of the process, we, of course, will restore the initial observation and schematic version of the droplet representation, and basically introduce the experimental setup that we had, and using a hydrophobic liquid, drop water on the surface, and he had a mathematical method and a model for the sorting of the theory, and a number of droplets per time was also investigated, and the alcohol concentration, he did have included the alcohol concentration. However, I think that he could use different types of alcohol, and he had investigated the alcohol evaporation, and it did mention the fact that how does the alcohol evaporate in the phenomenon. And we had, and the reporter had investigated the Marconi flow velocity. And for the reporter's evaluation, the strong points, he did have different types of oil, including sunflower oil and the olive oil. And he had analyzed the data, and there was a comparison, but there would be a consideration of the effect of the Marconi effect, which is the main water theory in this phenomenon. And for the area of improvement, as I mentioned, there was a data analysis which did give us a clear comparison between the theoretical result and the experimental result. And I think that there was not a clear restriction of the evaporation in the initial observation of the experiment. And it could mention the effect of the temperature of the water on the theoretical model and the experiment. And then value the types of the liquid that we had. And there was also that I mentioned there was a lack of comparisons, and I didn't see any mention of the fact that there was a unit for the diagrams that we presented on the report, and didn't have the variation of the type of liquids that we used. And now for the opponent's evaluation, for the strongholds, we did ask about the oil's thickness, which I mentioned for the cylindrical shape of the droplet, which was the base of the theory. And he did ask about the concentration on the edge of the droplet. And also there was the fact that the oil was included, that which covered what kind of oil you can consider in this phenomenon. And also, he also mentioned the latent concentration, and also clarified misunderstandings that we have from reports, such as the size of the droplet and type of the liquid. And for the areas to improve, he could ask about the shape of the model for its asymmetric or symmetric shape. And for discussion points, we had oil thickness, which I agree with the opponent. And the evaporation concentration was also mentioned in the discussion, and also in the utilization of the size of the droplets was also mentioned that the reporter also asked, which I would still agree with the opponent. And we had also the opponent asked about the emerging fingers of the droplet chain. And also he did mention the effect of the oil bath on the surface tension. Thank you for your attention.
All right. We will still have 2 minutes time for concluding remarks.
Hello everyone. So for my concluding remarks regarding this discussion and the reviewers report over here. First of all, I'd like to start with our discussion with the opposition. The opposition did present a lot of what I think really good points, but most of them I believe were already mentioned in some capacity within the presentation. For example, let's just take height, for example, which was mentioned in the Marconi velocity, which was then calculated as well. So I mean that's just one thing, one contention that I have with the opposition. Other than that, I believe that they really helped me clarify my own theory really well, because like this is such an amazing phenomenon that 12 minutes is just not enough time to explain and go into depth about everything. So furthermore, about the reporter's report, they said that a lot of the sites were missing their units, but those were mostly because of that they were regarding the number of droplets themselves. And so you don't really have units for number of droplets, it's just number of droplets. So that's one thing there that I'd like to mention. Other than that, I believe that this parameter discussion was really helpful for me, and that it allowed me to explain my own theories and beliefs in greater depth than before. So thank you.
Thank you very much. We will have 5 minutes time for questions from the jury. So please put on your and we will just give it a second and not like stress it out. Alright, then maybe I can have a quick question myself first. So you did your analysis with image J to count the number of things. And my 2 quick questions. So first of all, did this work for all parts of the phenomenon, or is there something critical? And secondly, do you have an image where you overlaid what you detected on the original image?
Overlay would be like on the original image.
You know that each droplet that gets fragmented is kind of labeled.
No, I don't actually.
Alright, thank you.
That.
Yeah, that's fine for me. And do we have any other questions? So Don, please go ahead.
Firstly, I would like to ask the opponent, you referred a lot of times to have the measurement of the concentration at the edge of the droplet. How do you physically do that?
I think you could, so by observing how the size of the final droplet changes, you can see, like for example, initially, if you wait very long, it will also only contain water, so you can see how the size changes and the percent that evaporation.
At that particular point, surely the concentration, you know how much oil and how much water is in a droplet. How do you determine that?
Okay, so there shouldn't be oil in this droplet, and you can just okay, and you can compare its size to the size you waited for a very long time. And for example, if this is like twice the size of the original size of the constant, then the outcome will be like the same value to the size to the amount of
Thank you.
oil.
And to the reviewer, I would like to ask the same question. You also referred to that. How would you measure the concentration of a droplet at a specific point in time?
Yes, you could make a range of time, and then by experimental result, when the droplet starts to get fragments, you can change. You can use the same range that the time that I mentioned, and use the model based on the surface tension. So.
Thank you. Okay, that's already quite good. So we will have another question from Sam.
To the opponent, you mentioned something about the reporter's model not being able to model the distribution of size of small droplets at the end. How does the distribution, how would you get a more narrow distribution of droplets, say, according to you, in physics?
Narrow distribution of droplets. So I think you can get, for example, you can get like a really high concentration, and all the droplets will just fragment really fast. So it will mostly just so the distribution will look more like this. It will just accumulate at the really small fragmentation, a really small droplet radius, and you get a large number because you fragment really quickly for large concentrations, and you will get like a really not sort of
All right, Sam is already satisfied with that. So do we have any other questions?
If no one else.
Okay.
So, question to the reviewer, you mentioned that at your questions, the percentage of carbon, how do you think affects this?
When you have a higher than 5 parameter in the output, that will affect the decreasing in the fermentation of a model droplet. So I think when we increase the number of after 5, we will have a decrease in fermentation.
Yeah, by the way, just as a quick remark, as a team, you are also allowed to say that somebody else should say something to the two-row question, so this is specifically allowed that somebody else gives us a quick comment. I would like to maybe take the opportunity to ask something myself. So, to the reporter, you assumed like on one slide that lambda equals 9 times
Yeah,
A.
yes, yes.
And the opponent criticized you a little bit, I think. So very quickly again state why you think this assumption is justified.
I'm doing it more.
I think that
I'll just state it. But yeah. So okay, I believe that at the edge of the mother complex, the rim actually forms a cylindrical circle of radius r. So that cylindrical circle, I believe, for very small amounts for very small lengths, so it can be assumed to be almost straight edge. So that is why I believe that that this ratio should hypothetically work. I did mention during my presentation though that I can do myself believe this is not a really accurate one, but this gets us pretty close.
Alright, thank you very much. Unfortunately, we're out of time for questions. Sorry about that. Next time you need to share and then you can ask your own questions. Alright, thank you very much for everybody. You can of course get seated again, we will do the grading and then we can continue. Okay, and we will see how to do it, but yeah, it's important just to. Perfect. So grading is done. Unfortunately, one of our viewers had to point it real quick, but Sam will hold up his grade, and then for the feedback, he will hopefully be here again. So, so first of all, we will do the grades for the report, please. We have a 3, a 7, a 4, a 5, and a 5. Then we will have the grades for the opponent. We will have an 8, a 7, a 6, a 7, and are you missing one?
Yes,
And a 7. And we will have the grades for the review. We have a 4, a 5, a 4, a 7, and a 5. Alright. Alright, so for the report from Pakistan, there's quite a spread between my 3 and Don's 7. Yeah, I mean, I'm definitely the negative bias in this juror group, and Don is definitely the positive bias. So if you don't know, jurors in the hierarchy have a certain bias, depending on how they grade to the average. And jurors with negative biases get grouped together with jurors with positive biases, so that the average roughly averages out. But, of course, there are also reasons for my low grade of 3. My parses are 1, then 1.25, and 0.75. And basically the reason is the following. I gave Garan a 4 in the previous round, and I think that roughly the reports are comparable. You had theory, but it didn't quite give you real predictions for your experiment. And you did some experiments, but they were quite unclear in the way you presented them. And this is both true for Iran, but I think yours was definitely more chaotic. And for example, the things that you did present, additionally to the things you grabbed from literature, were fairly unclear, because you should have definitely spent more time there. Because like this is the thing that you did, right? I know the paper because we did, of course, the same thing, right? I think everybody read the paper, and it would have been fine to go a little bit quicker through that and spend more time on the stuff that you try to go into the that you try to do for the problem. Also, it's important. There are a few very critical things about this phenomenon, right? Because your experimental stuff looked nice, but for example, like measuring all these droplets is something which I consider to be fairly complicated. So it would have been important to show that your analysis actually matches your experimental data by overlaying them once. Because at least like towards the end, all these droplets are like this small and they merge together. So things can get really quick, really strange, and it would have been great if you like supported your own work a little bit better, because I like to give the benefit of the doubt, but of course if there are many things where I have to give the benefit of the doubt, at some point it just runs out, right? Alright, so that was my grade, and then we'll have the 7 from Don.
So I'm also obviously trying to keep in line with what my bias is, to not disadvantage anyone. I thought you tackled a really difficult phenomenon. I think you communicated it really well when I looked at it. As a teacher, you really know what you're doing. You were able to explain it in terms of the art. I get it. I do think there was lack of some error analysis. The theoretical prediction seemed a little bit overly simplified, I'd like to see. And the way you worked on the board, I thought that your discussion was great. You were confident, you weren't overconfident, you listened, but you did really well in the discussion. So that's why I graded you.
All right, thank you very much.
Yes, of course. Just for the presentation, I would suggest that you press on your own to change the slides, because that's also some interruption in between. Take the presenter will be more smoothly presented.
That was definitely one of the more chaotic things. All right, then for your position, we have highest grade of data, which I will comment afterwards. So I'd like to do the negative things, or the lower things first, sorry. So Sam, you would should lead on your 60s.
I think it was a good opposition. It's stronger than the grades given for the board reviewers. I think you won this round. I would like to maybe to focus more on, and it was very good to show. I think think, a deeper understanding of the phenomenon, great. But I would like to focus more on, a bit like you said, the experimental details and the error analysis. And also, you spoke a bit too fast during the opposition speech. Try and slow it down. More is less. But well done.
All right, and then did you read off your classes? Sorry.
1220.
All right, thank you very much. And then we have my highest grade of 8 for the opposition. And I mean, compared with the previous opposition, I thought it was better. I didn't quite understand why my grading sheet turned out to be 2 points better, but that's just sometimes how it works out, right? So I gave you the default 1.5 for questions, 2.75 for your speech, and 2.5 for the discussion of the report. I think definitely like the opposition speech really pointed out many of the problems with the report and many of the things that I actually written out. So of course this is also always something if you happen to like criticize everything that I would like to ask afterwards, and for my feeling of course this is very good. And in your discussion of the report, this was of course also good, otherwise I wouldn't have given you so many points, but I would like to criticize one thing just because I criticized it for Pakistan as well. Try to get a little bit of a discussion going. Also, it was partly also a monologue, and you trying to like tell us the correct physics instead of working together to arrive at the correct physics. No matter if the physics turned out to be actually correct, just as a field.
So I'll just make one excellent opposition. You did, however, you stated your goal of your discussion with a whole lot of points, but you didn't get to them. And you got deep into a certain section. When I looked at what your goal was, I felt that you maybe didn't spend enough. You spent too much time on some aspects, not enough on what you came to, which is a constructive criticism. Well done.
All right, thank you very much. And then for the review, we have 2 4s. So maybe Sam can say something. Sorry. So maybe Sam can say something to the 4 for the review.
Yeah, I didn't think that you had evaluated both the report and the opposition enough. You went through the pros and cons prioritization, you didn't evaluate it as well, I thought, and you had some of your own opinions there, but I think you were a bit, it wasn't as strong as I expected, so not on par with the report, I would say. So yeah.
I agree that in general your own opinions were rather shortly stated, and it's also only orally, so for example not in slides, and also your slide points were rather generic, so you had points like had analyzed data, didn't calculate certain parameters, but you also didn't fill this up orally. I mean, it's fine if it's like a little bit generic on the slides, but then you like make concrete points in your oral speech, but that was a little bit lacking. But then we have, on the other hand, we have just in 7, so please some positive remarks.
So, my questions are 1.5 to 1.5. I like the question that you have asked, like the content of the pattern. And then I like your discussion answers. You also mentioned the temperature and symmetry of the system.
All right, thank you very much.